Hi, I'm Anindo. I'm back again with exercise 7, activity 5. In this activity, we are trying to generate a set of normally distributed or Gaussian distributed random numbers, starting with a set of uniformly distributed random numbers. So, first, I would like to tell you that this is not a pedantic exercise. There are many natural events which are either distributed normally or which approximate a Gaussian distribution, and it's a useful tool to know how you can transform a, a uniformly distributed random number set of random numbers to a Gaussian distribution. So the process that we are going to follow is formally known as Box-Muller transform, and you can read up about it in Wikipedia or elsewhere. And in this video, we are going to focus more on the programmatic aspect of this process. In the first part of this activity, we are going to use rand function to generate a matrix with two rows, each containing a million random numbers between 0 to 1. Uh, but it's difficult to show a million numbers on the screen, so I'm going to choose a really small number, say 10, and we are going to uh, do this procedure on the small matrix. So here we have a matrix with two rows, each containing 10 random numbers between 0 to 1, and we are going to, as is asked in the second part of the activity, we are going to stretch this distribution, which is between 0 and 1, to a distribution between -1 and +1. So you can imagine that this interval is becoming twice as big, and the beginning point instead of 0 is -1 this time. So let's store this new distribution into a matrix called trials, and that would be given by this rand 2 comma 10, and we want to multiply each element of this array by 2, and the starting point is -1 instead of 0. So then we have this new distribution, which is between -1 and +1. So in the next part of this activity, we need to square each of these elements and sum them up in pairs and see whether they add up to more than 1 or uh, less or equal to 1. So let's store them in an array R given by all the pairs, and remember, each time we're doing array multiplication and not matrix multiplication, so remember these dots. Oops. Now that we have the vector r, we want to multiply, we want to find the factor which we are going to call temp, uh, which is square root of twice negative twice logarithm of r over r, and we are going to multiply each of these elements with that factor. So let's have temp equal to square root of -2, and again it's array multiplication, so star log of r over r, and that gives us predictably complex numbers, because you can see whenever we have r between 0 to 1, we have a negative number, so that multiplied by -2, that gives us something positive, and we have temp as a real number. On the other hand, if we have r greater than 1, for example here or here, we would end up with a positive number for the logarithm part, and that multiplied by -2 is going to give us a negative number, square root of which would give us an imaginary number. So we did end up with a fair number of imaginary cases like here. So the next step would be we want to multiply each element of this matrix trials by the factors of temp. So let's call this new matrix shifted, and that's given by trials, again array multiplication, and we are going to multiply by a 2 by 1 array, each of which would be temp. So here we have the shifted matrix, and as asked, we are interested with the cases which are completely real, which meaning like which do not have this imaginary part. So for example, these numbers would not be there, so we can choose the real part of shifted, and we do see that many of them are zeros, so which were originally completely imaginary parts, like these, and it is given as a hint in the exercise. So we can use the non-zero function, and let's store uh, the newly generated numbers as new rands, and we would just choose the non-zeros of the real part of the matrix, of the shifted matrix. So here you see we just have a vector with just a non-zero real elements. So next we are going to plot a histogram with these numbers. So now that we have played around with the programmatic part of this activity, we can plot the actual thing. But before doing that, we should probably go to the real size of 1 million data points rather than 1 million random numbers, rather than working with 100 numbers, because, or in fact 10 numbers, because that's for sure not going to give us a good normal distribution. So let me retrace all the commands that I have given before and increase this from 10 to a million, and I for sure don't want to print this on the screen. So we have the trials function, and then we want to get the squares of the uh, pairs of random numbers, and then we want to have temp, which we multiply to get the shifted array, and then we finally generate the new rands, which considers just the non-zero real numbers of the numbers that we already have. So this is what we have done so far, and now we want to plot a histogram with new rands, and we can generate that with the function hist. So we are going to have, apart from the histogram, just the bins, we also want the midpoint of the bins, because later we want to plot that and compare with a normal distribution. So here we have n, and let's say x out, that's the midpoint of the bins, and we have function hist, which would take new rands as the input, and we have 100 bins, and we want to plot this with a bar diagram. So let's say we have bar with x outs and n's. So here we have our normal distribution with the numbers we have, but to see if it's actually a normal distribution, let's plot a line which we know, which follows the formula of normal distribution, and we would overlay that on this plot to see how they match up. So let's create some. Oh, before we move on to that, we want that plot to be on this bar diagrams. So we want to hold on to this plot, and then we want to create a set of x-axis values which are equispaced, and let's say we start with x going from -5, oops, with an increment of 0.1 up to +5, and we have the corresponding y values, and this where the normal distribution comes in. So we have the length of the new rands array, which gives us the n dot, the total number of points that we have in a normal distribution, and we multiply this array with the bin size, which is delta x, so that we can get as x out 2 minus x out 1, and then we want to divide that by square root of 2 pi, and multiply the whole thing with again array multiplication, exponential minus x square over 2, and finally we want to plot this result, which would come over the earlier result, and if you look carefully you'll be able to see this blue line which was not there before. In fact, you can see it's hugging all the midpoints of the bar diagrams of the bars, but and reaching up to here. So you can see we have produced a pretty nice normally distributed set of random numbers, starting with um, uniformly distributed random numbers, and we verified that with our standard expression for Gaussian distribution. So this is what, as I told you, is the Box-Muller transform, and I hope it helped you understand what's going on here, and we'll see you in the future in a different exercise. Bye.